Okay, so hopefully you're coming off the theory discussion where we talk about factors of safety and what they represent and how they start to help us understand an appreciation for uh, issues with materials or estimating loads or estimating resistances. And so this is a simple example to show that. I will put the card up there to the theory lecture in case you missed that. It's probably worth a few minutes for you to follow along. So in this case, we've just got a axial rod, uh, rectangular of some sort. So it's 40 millimeters wide and it's got a depth of X shown. And basically what it says, we want to use a factor of safety of 2 against yielding, and then we give the yield capacity of the material, which is 310 megapascals. And so what it wants to know is what is the minimum thickness or depth of X that we need if we want to resist a load of 120 kilonewtons. So the first thing I want to do is I want to figure out what my allowable stress is. So my stress allowable. And this is really where we will apply our factor of safety. And we're going to apply our factor of safety against the material properties. Okay, so stress allowable is really equal to, in this case, our factor of safety is against the yield capacity, and you could have different factors of safety against different criteria. And so we're going to go stress yield divided by our factor of safety, which is equal to 310 megapascals divided by 2, and gives us an allowable stress of 155 megapascals, which we're going to carry forward into the next part of the problem, which is how much or what thickness of rod do we need to resist that 120 kilonewton load if we don't want our stress to exceed 155 megapascals. So we'd absolutely do a free body diagram, method of sections, whatever you want. We see that the internal force in this rod is 120 kilonewtons in tension. So that's your method of sections, if you will. It's a little bit trite in this case, so I'm not going to do it out deliberately. I'm just going to go right on and start to determine our depth x. So in this case, we know that our stress allowable has to be set equal to the load that we're applying, 120 kilonewtons, divided by the area. Now, the area itself, so I'm going to say where our area we know to be equal to 40 millimeters multiplied by x. And so we can substitute 40 millimeters times x in for area. So I'll do that is equal to P over 40 millimeters times x. And we can substitute in for P. We know P is equal to 120 kilonewtons. So we're working again in millimeters, so probably better to do that in as 120,000 newtons. And our stress allowable is, stress allowable, and we'll set it equal to our 155 megapascals. And we can isolate for x and solve for x, and we can get a value of 19.4 millimeters. Now, just as a practical point, we're not going to specify 19.4 millimeters depending on the material, the sections, what's available in your area. You're going to round it off to the next reasonable increment that you can buy on the market. And so in this case, you're probably going to say, use an x equal to 20 millimeters. Now, important there, it would be inappropriate to round down because you'd be getting smaller, in which case you'd be exceeding 155 megapascals, so you have to round up because that is more conservative. So we're going to round up for conservatism. And there we go. That's a simple application of the factor of safety. Really, what applying them isn't that difficult. Understanding them is worth a listen. So again, at the end of this video, I'll put on a quick link just in case you did miss the theory bit associated with factors of safety. I strongly recommend you go back and pick that up. And I think that actually brings us to an end of this series on axial load. And we'll be looking at torsion coming right up.